So we are dealing with force in Newton's second law. Already we derived this expression, F is equals to ma, or force is directly proportional to rate of change of momentum. That also we have written in the last page. We have written F is equal to dp by dt, rate of change of momentum. Now, so what we have to say about force is, so as usual, what we learn in school level, force is an external effect. Force is an external effect in the form of push or pull. That we can say. What we can say? Force is an external effect in the form of push or pull. Right? So when we are pushing or pulling, what happens? It will try to move an object which is at rest. Right? It try to move an object. Try to move an object which is at rest. Right? Now, next. Next, what else we can say? It is trying to move. That means the object may move when it gets sufficient force to move it. Otherwise, it may be at rest only. Next, one more thing what we can say, if the object already, if it is in motion, we can stop it, right? We can stop it, or it may try to stop it. So tries to stop moving body, right? Tries to stop moving body. This is one more thing the force can do. And one more thing we can write from here, if any object is moving in one particular direction, and the force can change direction also. Okay, it tries to change direction also. It tries to change direction, right? So these many ways force will be effective. Okay, it is an external force. Sorry, it is an external effect which will cause push or pull, right? And it may try to move any object which is at rest. Okay, it may try to stop moving object, or it can try to change the direction of a moving object, right? So all those things, the force can be done. Now, and in notes I'll be giving you a clear example with one table, various how various conditions will be there, like if any object, if it is at rest, if we apply force, so what happens is the change of a state, sorry, the change of state may take place. That means if it is at rest, it may be moving. Means all those I'll be giving you with one clear example with a neat diagram. Okay, one table I will be framing there. So I don't want to go with those diagrams clearly again. So because already I explained here how it will be. Directly we will go with the next part in this. This is how force will be. Next. So what are the dimensions of force? That means what is the formula of force? Already we have written. Mass into acceleration. Right? Next. So what is the dimensional formula? Did we write dimensional formula? I think no. So dimensional formula is what? Mass dimensional formula is m, and acceleration is L t to the power of minus. This is dimensional formula of force. Right? Now, and this is dimensional formula. Next, what else we can write? We have already written units. Once again, I'm writing here. Anyhow, we are discussing in detail about the force. So I'll be writing here units. If we write units, so SI unit we have written already. I'm just writing quickly. SI unit is what? Newton, we said. Right? So actually, it should be written in small letter only. Okay? But how we will represent 1 Newton or 1 Newton, right? We should not represent with capital letter. Now, so 1 Newton means what? 1 Newton is equals to what we have written? 1 kg meter per second square we have written, right? Now, and what about CGS system of unit? CGS system of unit also we have written. No? So that is, see, in CGS system we called it as a dyne. CGS. In CGS, what is that? Dyne. So we have written conversion also. Let me write 1 dyne is equals to what? 1 gram centimeter per second square. And what about conversion? Conversion also we have written 1 Newton is equals to 10 to the power of 5 dynes we have written. Right? So this already we have completed. That's the reason I'm moving quickly. And what else we can mention here is this force can be represented in terms of newtons, or it can be represented in terms of dynes, or it can be represented in terms of kg force. Okay, so kg force also we will represent whatever weight we measure, we will be measuring in kg force only. Okay, so 1 kg force means how much? 1 kg force means how much? 1 kg force means 9.8 newtons. Okay, the same thing, 1 gram force also we can write. In CGS system, if we write 1 gram force, if we write 1 gram force is 980 newtons. How this has come means acceleration due to gravity value will be using. Acceleration due to gravity G value is 9.8 meter per second square. When we are using in SI system, G is equals to 9.8 meter per second square will be there. Or in CGS system, if we use G is equals to 980 centimeter per second square. This we will be using that. How we will be using it? What is the formula of force? F is equals to ma. Okay, F is equals to ma becomes F is equals to mg. Okay, F is equals to mg it becomes. So when the force is purely gravitational force, then we will be taking acceleration as acceleration due to gravity. Acceleration due to gravity on the surface of Earth, we will take it as a 9.8 meter per second square or 980 centimeter per second square. Okay, depends on what unit we are considering there, right? So this is also one more unit. When we are solving problems, mostly most of the problems they will be given in terms of kg force or gram force, right? Next, one more thing here I have to mention. This F is equals to ma. Whatever we are writing, F is equals to ma, right? This formula, this is valid. This formula is valid only if force is changing the state of rest or motion. Okay, and the body is constant and finite. Okay, if the body is if the body is not constant, if it is changing, if it is not finite, we cannot apply this. That means very very minute particles like electrons, newtons and all, they will be having mass, but for them we cannot apply this easily. So microscopically we cannot analyze the Newton stuff, and if it is very huge also we cannot apply this. That is what it means. Okay, next, force generally along x, y, z three-dimensionally. If we are watching it, suppose if an object is there, suppose one stone is there and we are throwing it. When we are throwing it, it will move in space, right? In three-dimensional it is moving. So in three-dimensional, if it moves, so what we can say about force? Force is a vector quantity, right? So if we represent that in three dimensions, fx into I cap plus fy into j cap plus fz into k cap we can write. Okay, so this is how we represent a force in three dimensions. In terms of its unit vectors I am writing. So of course we can write this acceleration also. Acceleration also in terms of vector form, how we can write ax into I cap and ay into j cap, az into k cap we can write. Okay, ax I cap plus ay j cap plus az k cap. In all the three dimensions we are representing acceleration also, right? Now, so this is what I said about it. Okay, next, 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 what we say is we can also say in terms of direction, as we are saying, no, force is a vector quantity. If we are taking in positive, like forward, if we take it as positive, backward we can take it as a negative when we are solving problem. Okay, positive force means force between two similar charges. We can take it as positive charge, positive force that comes in electricity part. If two charges are there, okay, then force between two similar charges can be taken as positive, and a negative force means force between two opposite charges can be taken as a negative. Okay, and out of so many forces, we can write one expression. The strongest force is nuclear force. Nuclear force is strong because they are interacting between very short range. Okay, so nuclear force is the strongest force. After that, next, electromagnetic force will be there. Electromagnetic force is stronger after nuclear force. Okay, this means it is weaker than nuclear only, right? Next, gravitational force is weak. Okay, So gravitational force is weakest among all of them, right? Because it will act between the objects, right? Between any object, between any two objects, gravitational force exists. So if it is very large, we will collide with any other things, right? Suppose we are sitting in front of our mobile and we are there. So obviously, according to universal law of gravitation, what should be there? Eh, with the mobile and for us, attractional force should be there. So it is not coming and hitting us, no? So why? Because that attractional force is very less. That's the reason they are those two are separated, right? So if it is very large, we cannot continue with any of our work, right? So this is a comparison between different forces, which is stronger and which is weaker. This comes in actually in first chapter, physical world also. Anyhow, that we have not covered up to now. So here again, when we are covering that, we will come to know about this, right? So we are watching about force. What are the strongest and what is the weakest force? Next, uh, if we take a ratio of these electric force and gravitational force, it will be around 10 to the power of 43 will be there. That is extra information. So it is not required now. Next, constant force means if the direction and magnitude of a force is constant, then such a force can be taken as constant force. That means, suppose if any object is there, what I'm doing, I'm applying force on it. Okay, some external force I'm applying. When I'm applying the force, when the object is moving, if if the applied force direction is same, only one direction, and suppose if I apply some 20 newtons, the 20 newtons, if it does not change till completion of its complete motion, then such a force we call it as what we call constant force. Okay, constant force is there means variable force also will be there. Okay, so variable force means what? When the object is moving, the force which we are applying, it will change continuously. Such a force we call it as a variable force. Okay, so the variable force depends on time. As time is changing, the force value changes continuously. Okay, like example, if we take gravitational force between two bodies, if we take, so the gravitational force depends on position where the two objects are there, whether they are on earth surface or whether they are on moon surface or where they are it. Okay, so depending on the position, the gravitational force changes. Okay, so gravitational force, it is a position dependent force, we can say like that. So there will be mm, electrostatic force will be there. That also depends on force. Sorry, that also depends on the position, right? How far they are separated. Okay. Again, in second year, it comes F is equals to K into Q1, Q2 by R square. We will be writing what? Force, electrostatic force. So here, how much distance of separation is there for them? Depending on that, our force will be lying, right? So that is how the force is there in electric charges. So it is depending on position, right? Distance. That means position, right? It is also position dependent. So gravitational force is position dependent. Electric force is also position dependent, right? So motion of Earth around the sun, okay, all those comes under the same case, dependent forces. These motion of Earth around sun or electrons movement in about around a nucleus, all those can be taken as central forces. Okay, so now we have seen constant force and variable force, position dependent force we have seen. Okay, and time dependent force will be there, and central force means like centripetal force I said no previously. So the force which acts towards the center. Okay, so like that, central force will be there, and some other force also will be there. Conservative force, conservative. Better, I will take next page. Conservative force. Conservative force means what? If under the action of force, that means if any object is there, some force is applied on it. Then under the action of force, work done in a round trip, if it is zero, then if the work is not followed by the path, usually when we are measuring work, what we write force into displacement, we write. It comes further also. So if the work is not depending on what is the path followed, then such a force we call it as conservative force. Okay, so gravitational force comes under conservative force. Okay, next, Common forces in mechanics is what? Weight, right? Suppose if any object is lying, so weight acts downwards. That is gravitational force only. We call it as weight. So what do we write formula for this? Mg we will write. W is equals to mg, weight, right? So next, normal reaction force will be there. If any object is there, if weight acts downwards, upwards, perpendicular to that normal reaction force R or capital N, we can represent it. Normal reaction force will be there. And if one object is there and one string is attached, simply one string is attached here, and we are pulling out of here. So what happens here? The force when we are pulling this side. So there exists some internal force inside the string opposite direction to whatever force we apply. That force which is present inside the string, we call it as a tensional force. Okay, that also lies, okay, inside the string. Right now, what we have seen here, some conservative force where the work done is not, if some work is done by some particular force, if the work done is not depending on the path. If it is independent of path followed, such a force we are calling it as conservative force. And weight of the body, we can take, okay, that is also one more kind of force, and normal reaction also one more kind of force, and tension present in a string also one more kind of force. Next, one more thing, the last thing which we will speak about force is spring force. Suppose if there is a block attached with the help of a spring. Okay. Now, if a block is attached with the help of a spring. Now, if we pull this block little bit, what happens? There some extension will be produced in the spring. Okay. So whatever force is present inside this spring, that usually that force we will write expression with F is equals to minus kx will write. Why we are writing this is how much we pull, that much it will return back. Restoring, that's the reason I kept minus. How do we write is this force, the force which is present inside the spring is directly proportional to kx we will write. Means how much we displaced it. So if we remove proportionality, we get some constant k. As it is opposite direction to applied force, that's why I kept one minus sign here. So F is equals to minus kx, we will write the force present inside the spring. How this has come means F is directly proportional to the displacement moved by us, right? Now, so what we call this force, restoring force we call, which is present inside the spring, which is restoring it. Okay. What about this K? The proportionality constant K, we call it as a force constant, we call it. Okay, force constant. Right, that is all about different kinds of forces which we come across. There are some other forces also in general, right? This muscular force will be there, that some different kinds of forces, chemical force will be there. All those we have studied in school level. Whatever I said, we will be studying further. Right? This is complete information about the force, and some little more information will be there. Concurrent forces will be there that I will explain. Then we can go with the Newton's third.